All right, last class we learned about ICE tables, and some of you may hate ICE tables, and that's perfectly understandable. We'll be getting to some stuff that's a little bit nicer, I guess, with ICE tables in just a little bit. First, though, this example problem. We've got a reaction given to us, we've got a Kp value given to us, and we've got some initial conditions as well that are given to us. So we've got partial pressures of 0.150 atmospheres for both of our reactants and no product. And we want to find equilibrium pressures of all three substances. We're also going to need our Kp expression to help us solve this problem. I already drew out the ICE table, and based on our coefficients, the stoichiometry that we have in our reaction, we can add in change values. So iodine and chlorine are both reactants, so they're going to be decreasing. So negative x, since they both have coefficients of 1. Our product has a coefficient of 2, so it's going to go up by twice the amount that our reactants go down. So our equilibrium values are 0.150 minus x for both of our reactants, and plus 2x, or just 2x, for our product. Now we get to plug all of those into our Kp expression. So we've got 2x squared up top, and we've got 0.150 minus x squared on the bottom. So 4x squared, and then we get to FOIL. So 0.150 squared minus 0.300x plus x squared. I'm writing 0.150 squared because I just didn't want to plug it in the calculator yet. And then we get to rearrange 81.9 equals 4x squared all over 0.0225, and this, and last but not least that. So we'll do 81.9 times all of those. This whole thing on the bottom, we have to move that over. So our denominator flips up. 1.84275 minus 245.7 plus 81.9 x squared. And that, of course, equals 4x squared, so we can subtract 4x from both sides, or 4x squared from both sides. And we get 77.9 x squared. So now we've got our quadratic equations set up. I just have them in the backwards order. CBA. Question?
Is it 245 or is it 24.5? It's 81.
24.5. Questions about getting there? Okay, and then if you've got a TI-36X Pro calculator, there's a built-in quadratic equation solver, which is great. So you can just do that, because I don't really care if you know how to solve the quadratic formula, like personally. Or you can use the quadratic equation. Let's see if it's still in the brain. Something like that, up in the top left. So you'd put that in, and we get out two values, and they're both positive. One of those x values is 0.1228 with some other stuff. The other x value, 0.1925. And some other stuff after it. There's only one equilibrium state, so we have to choose the one of these that makes sense given our problem. So we're looking at our equilibrium concentrations for iodine and chlorine. They're 0.150 minus x. If we subtract 0.1925 and the other stuff, we'll end up with negative numbers for concentration, which we can't have. And so x1 is our solution here. So for our equilibrium concentrations of iodine and chlorine, they are 0.0272 atmospheres and for I.C.E, something like that. Questions? All right, fun with ice tables. Sometimes we don't have to do a whole ice table with all the numbers in there. Sometimes we can just ignore the x. And so that makes things really nice. We can just make an approximation that x is really small, and so it's not going to affect the numbers or some of the numbers, the change numbers, very much. And we don't have a significant loss of accuracy. If our initial reactant concentration is large, we can assume that x is small and just toss it out. To check that assumption, a good rule of thumb, the rule of thumb from the book, is comparing the calculated value of x to the number it was subtracted from. It should be 5% or less. So if our change number, if our x number is 5% or less compared to our initial concentration, we can just toss it out, which is cool. So using that x is small approximation, consider this generic equation, A in equilibrium with 2B. We've got a K value given. If our initial concentrations are 1 molar and our concentration of B is 0 molar, what are the equilibrium concentrations? we've got K equals concentration B squared over concentration of A. We've already filled out our ICE table. .3 times 10 to the minus 5 equals 2x, and that is squared, over 1.0 minus x. Normally, what we would do here is swap our 1 minus x over to the left side, and then we would get to have fun setting up our quadratic equation, plugging it into our calculator, or doing it by hand. Our k value here is really negative, or really small rather, negative exponent. That indicates that our reactants are going to be favored. We're not going to have very much product. So this reaction is probably not going to shift very far away from our reactant. This is one of the instances where we can use the x is small approximation. Your book has examples of how to do those 5% comparisons. So if we say that x is small, we get rid of the x. And this simplifies to 3.3 times 10 to the minus 5 equals 4x squared. Divide both sides by 4. And x squared we can turn into x equals square root of our k divided by 4. And we get an x value of 0.00287 molar. So if x is small, then that's our change in concentration. If we compare this molarity value to 1, we're looking at 0.29%. Which is less than 5%, so we can keep that. So that saves us a ton of time, and you could probably, like, if you want to, you can go ahead and run it with the full quadratic. It probably doesn't really change. Questions about using that? It's nice. All right, consider the reaction for the decomposition of hydrogen disulfide H2S. We've got initial values given to us. Find the equilibrium concentration of S2. You can use the small k approximation. All right, we're able to use the X is small approximation here. We've got our reaction mixture, we've got some of our product, some of our reactant, not in that order, and also none of another product. Our ICE table. We can set up initial concentrations. I'm leaving off the molars. The problem has enough teeth without them. Our change values for hydrogen disulfide, dihydrogen. What? Anyway, our concentrations here, we're going to lose 2x. For H2, it's a product, we're going to gain 2x. And for our last one, we're going to gain x. Since we don't have all of our reactants and products present, we don't have any S2, our reaction cannot proceed to the left, it has to proceed to the right. That's what my brain was like, wait, do we have to check that? No, we don't. Okay, so 0.100 minus 2x, 0.100 plus 2x, and x. We set up our Kc, concentration of H2 squared, concentration of S2, over concentration of H2S squared. We pop in our E values and see what a big mess this would be if we couldn't use our approximation. It would be something like that. This is a very convenient spot for us to use our X is small approximation. So if X is small, we can get rid of both of these X terms, the change terms, and we've got 0.100 squared over 0.100 squared. So those two terms completely cancel out. Substitute in our value for Kc. That is equal to x. Huge time save. And then we can check, is our x actually small? So we compare our x value against an initial concentration value. Of 0.100. And we'll end up with a nice small number. .000167%, much less than 5%. So our X is small approximation is good here. So our equilibrium concentration of X2 should be right around 1.67 times 10 to the -7 molar. Pizza cake. Okay, so we've seen two instances where x is small works. Let's look at another situation. So this is the same reaction. It's the same Kc. What has changed here, though, is our concentrations. We've got some of our H2S. We don't have any H2. We don't have any S2. And the amount of H2S that we have is much smaller than in the previous problem. We are still going to set up our ice table. So an initial amount of 1 times 10 to the minus 4, 0, and 0. Our change values are the same, minus 2x, plus 2x, and plus x. Giving us these as our equilibrium values. Set up our Kc expression again. Plug in our equilibrium values. Should end up with something like this on the right side. Now let's assume that x is small and simplify this out a bit. We'll have 4x cubed over 1 times 10 to the minus 4.
Do we square the 1 constant and make it 4 or no?
Yeah. That is squared. So after doing a whole bunch of rearranging, we get x cubed equals this whole mess. So you can evaluate that and then plug it into a cube root, or you can cube root it all at once. And then we'll get a value for x.
Isn't this supposed to be times 1.0 and 10 to the negative 4? Can you take the other side or no? And then divide the whole thing by 4?
Yeah, it should be times. Cool. I was wondering what was happening. It looked too big. I'm keeping everyone on their toes today. Or at least, I'm keeping one of us on our toes. it should be a pretty small number. Okay. I got, after some calculator fun, this. That is the same as, I think that's -6. And now we get to check if our X's small approximation works. So 7.474 times 10 to the -6 over 1 times 10 to the -4 times 100. And it's 7.47%, which is greater than 5%. So we wouldn't get to use our X's small approximation here. Although, me personally, I would say it's close enough. I'm not going to do the extra work. But I'm also not getting points based on whether I make that approximation or not. So that will happen sometimes. And then we would have to do it the old-fashioned way with the polynomial. Questions about that?
How did you get the 7.47%? Because I got something different. Like when I took the cube root.
The 7.47% is from the 7.47 times 10 to the -6?
Yeah, like when you got the 0.000. Because I got like 3 zeros and 16022. I don't know if I put it in wrong.
You could have put it in wrong, but that would also be an even bigger number, and then you'd still have to go back and do it anyway.
No.
But yeah, too much going on for me to make a good educated guess about what might have happened. So if I remember when I'm making the exam that covers this, I'll either give you one that this small X approximation works, or it just like it won't, and it'll be pretty clear that it won't. If I'm remembering, so that it's not like too tough. All right, given this generic equation, take a peek at each of these K and initial concentrations and make a guess about which of these most likely will work for the X's small approximation. What sort of conditions do we want for X to be small relative to our initial concentration?
Our initial concentration should be like bigger.
Yeah, we want a big initial concentration. So that's going to be either A or C. So that leaves us two choices for K values. Is a big K value or a small K value going to favor?
Small.
Yeah, we're going to want a small K value. At least in this case, because we've got our initial concentration being for our reactant. So if we have a really small K value, that's going to strongly favor our reactant. Since we're starting with only reactant, that means we're not going to lose very much reactant. It won't have to shift very far away from where we started. And so our correct answer here would be A. You would get a different answer if it was concentration of B instead of concentration of A. So these are some things to look for when you're thinking about, can I use the X is small approximation? Some other notes about equilibrium things. Our concentrations have to be in moles per liter. Our good friend, molarity. Our partial pressures need to be in atmospheres. And it's important to use the correct equilibrium constant. Sometimes they're the same, but not always. And our X is small approximation doesn't mean that X is 0. It just means that it's really close to 0, and so we're not losing that much information. We're not being that inaccurate by ignoring it. So we can ignore it without losing too much accuracy. This is like when you ask how tall somebody is and they tell you they're 5'10", but they're really 5'9 3/4". They're basically 5'10", so you might as well just tell them 5'10", because 5'9 3/4 just takes longer to say. Nobody really needs that extra information. All right, that'll do it for ice table stuff for this chapter, at least. So moving on to a principle that you hopefully covered in at least 3A and maybe also in 1A a little bit, Le Chatelier's principle. Le Chatelier's principle, there was a quote from Le Chatelier at the start of the chapter, is the idea that a system that is at equilibrium, when it's disturbed, shifts left or right to minimize the disturbance, to reestablish equilibrium. There are a bunch of things that you can do to screw up equilibrium. Closing your eyes and spinning around in a chair will do it. It's messed my equilibrium up before. A possible example using two countries. If country A and country B are both at equilibrium. They've got a nice even rate of flow of people emigrating between the two countries, and suddenly a bunch of people pop out of a wardrobe. People start flooding into the country of B from a magical mythical wardrobe. Now there's extra people in B. And some of those people are going to say, it's too crowded here, get me out of B. And they're going to move into country A to try to get away from some of the new weird people with like goat bodies that are coming out of the wardrobe in country B. It's a Narnia reference. Mr. Tumnus. So a couple of things that we can change. The first one that we'll talk about is a concentration change. So if we change the amount of chemical that we have, if we just dump in some chemical, that's going to cause our equilibrium to be upset. One of the simplest ways to think of this is if we add to one side, it's going to shift away from what we added. That's the simplest way to remember it. So if we're adding NO2, that's our product here. If we add NO2, it's going to shift, and the rate to the left is going to increase. We've got extra stuff on the right side, so we need to get rid of some of that and shift it back into reactant. Another way that we could evaluate this is with our reaction quotient. So remember that our reaction quotient is the same sort of expression as our K, our equilibrium constant. It's just at any state. It's not only at equilibrium. So like if we had, I'm not even going to make up numbers, but we increase this top number, our Q is going to get bigger, and our Q is going to have to shrink, get smaller, to get back to being equal to our equilibrium constant, meaning that we're at equilibrium. So our NO2 concentration got bigger. We need it to get smaller to get our Q down. Again, the simplest way of thinking of it, just we added to one side, it'll shift away from that. Here's models of what that might look like. So if we have a reaction that's at equilibrium, we add in some NO2. Our equilibrium is disturbed, RIP equilibrium. Now we have extra of our NO2. The reaction between the NO2 molecules is going to increase. So probably the better, more mechanistic way of thinking of it is that increasing concentration increases reaction rate. We're only increasing the reaction rate to the left, though. So our rate of reaction from reactants to products has stayed the same, but we've made the reaction in the opposite direction faster by increasing the concentration. So we're going to see an overall shift from products to reactants. And then at some point, we'll reestablish equilibrium. We can also add reactant. And just like before, that causes it to shift away. We've increased the forward reaction rate. Shifting away from what we added. And here's what that might look like as a graph, in case you wanted it as a graph. We've got two options here. We've got both of them having time as the x-axis, so as we're moving left to right, we're moving through time. Our concentration is on the y-axis. And we've got our original equilibrium in this left section, a change happening at this first dashed line. So in our example A, we've got our NO2 concentration. We spike our NO2 concentration. That's our product. So NO2 concentration goes up, and it'll slowly decrease the concentration as it shifts to the left until we reestablish our equilibrium. And then B is just adding in reactant instead of product. Showing those concentrations slowly changing over time. So we talked about increasing concentrations. It'll shift away. Our equilibrium or reaction, if we decrease a concentration, it shifts towards the side that we decreased. We've removed some of our reactant, we've removed some of our product. You can think of it, oh, now we've got extra space there to produce more of that. In terms of our country analogy, if we just removed half of the population in country A, that's a lot of free real estate. People are going to start emigrating from country B to take advantage of some of that wide open spaces. All right, we have this reaction. It's in chemical equilibrium. What happens if we add bromine to the reaction mixture? What happens if we add BRNO to the reaction mixture? If we add bromine, it'll shift to the left. We've got extra product. We're going to increase our reaction rate in the opposite direction. If we add BRNO, it's going to shift away. We're increasing our reaction rate. So shift left, shift right. Questions so far about Le Chatelier's principle? Great. I thought about just not even lecturing on it but might as well. All right, pressure and volume are inversely related. Think in PV equals nRT. If one of these goes up, the other goes down. If nRT is constant. So if the volume of a reaction mixture is changed, the pressure also changes and the system shifts, again to minimize the change. We're going to make some assumptions about temperature being constant to let us use that idea. So let's say that we've got this reaction in a cylinder with a movable piston, so we can change the volume, we can change the pressure. What happens if we push down on the piston? If we compress the system, what happens to our volume? Volume decreases. So what happens to our pressure? Our pressure increases. This is like squeezing an empty water bottle so that you can shoot the cap at your friend or into the air. So we have an increase in pressure. How can we relieve the pressure? We could increase volume. That would be one way to do it, but without moving our piston. What's another thing that we can do to decrease our pressure? Our pressure is based on the number of particles that we have. If we can decrease the number of particles that we have, that'll also decrease the pressure. So it can be relieved by reducing the number of particles, the moles of gas. So what we're looking at here, we're assuming some ideality. We've got reactants, we've got products. On the reactant side, we've got N2 and 3 H2s. So we've got 4 particles on the left side. On the product side, we only have 2. So we can make this system take up less space if we shift the equilibrium to the right. If we make more NH3, more ammonia, those ammonia molecules are more compact. We've crammed more atoms into smaller number of particles, and so that's going to help lower the pressure. So our system shifts to the right. Because we have fewer number of moles of particles on the product side versus the reactant side. That's our more compact way of shoving all of the atoms into the same space. If we did the opposite, if we increased the volume, decreasing the pressure, making more room for particles, then things would shift from the ammonia side, the product side, over to the reactant side. Shift the other direction. Another way that you could think of this is on the reactant side, we've got 4 particles. There need to be some reactions that happen there. Those particles need to collide with each other. If we compress the space, we're going to get more of those collisions to turn into our ammonia. And if we increase the space, it's going to take longer for those nitrogen and hydrogen particles to find each other. And so that's going to decrease the rate of reaction in the forward direction. So we'll have a shift to the left. What would happen, though, if we added helium gas to this mixture without a change in pressure?
Shift right.
Shouldn't shift at all, because we don't have helium. Oh, wait. No, that would also increase the pressure, sorry. It would shift right. So yes, it would shift to the right because we've increased the pressure. Even though the helium isn't involved in the reaction, I think that would still shift right. Here's some graphics of what that might look like with the moving pistons. If we decrease our volume, increase our pressure, we're going to shift to the smaller side, the side with 2 moles of gas. If we decrease the pressure by increasing the volume, we're going to shift to the side that takes up more gas. We're basically finding the reaction mixture that best fills up that space without being too compact or too spread out. Oh no. I was wrong. Adding an inert gas at a fixed volume has no effect because it doesn't play a role in the reaction. Womp womp. There's also no effect if we have an equal number of moles on both sides. Because they take up roughly the same amount of space. In the real world, there probably is a small effect, but I would guess that it doesn't matter. All right, what's the effect of decreasing the volume on this reaction mixture? Think about it for a second, and then also think about what happens if you increase the volume of the reaction mixture. All right, if we decrease the volume, what happens? The reaction shifts to the right. Why does it shift to the right?
Increase in pressure, so it shifts to the less particle size.
Yeah, we have 3 moles of things on the left side, on the reactant side. We've got 2 moles of things on the right side, on the product side. If we decrease the volume, that's increasing the pressure. And we're going to shift to the side with less particles, which is the right. What happens if we increase the volume of the reaction mixture? That's right, it's the opposite of everything. Decrease the pressure, shift to the left. This would be like if you were studying down in the math center in the library and all of the tables are full. You might cram down into the fewest number of tables as possible, but then if half of the people that are there leave, you'd be like, ooh, pretty tempting to not sit smushed together with a bunch of other people. I'm going to go take one of those empty tables for myself. Similar concept, it's just that atoms and molecules are doing it. Temperature change can also affect a system in equilibrium. We can think of heat as a reactant. Which would be an endothermic reaction, or as a product, in which case it would be exothermic. And we're going to make an assumption that we have constant pressure, since heating things up would also change pressure. So we're assuming like maybe we increase the volume if we increase the pressure or increase the temperature. So the way that a temperature change can affect things is you might be told, for example, that you have an exothermic reaction. So you would write in plus heat on the product side. That would not be given to you. So you can write that in if you're told that it's an exothermic reaction. So if we know it's an exothermic reaction, heat's a product, and it's just the same as our concentration change. So if we add heat to the reaction shifts to the left, towards the reactants. We also have the fun side effect of the equilibrium constant changing. If it's an exothermic reaction and we remove heat, again, you write in the plus heat part. If we remove heat, it shifts from the left to the right. And this is going to result in us having a larger K. You don't really need to write in the K equation necessarily to see this, but since we're removing heat, we're shifting from reactants to products. So we're producing more products. The top part of our K expression is getting bigger, so K is getting bigger. In the previous example, we were shifting to the left, so we were increasing the reactants, and so we would see our K decrease as a result. On an endothermic reaction, it's the opposite. So you would write in the plus heat part on the reactant side. If we add heat, we're shifting away from the heat that we added. Just like with a concentration change, if we remove heat, we shift towards the side that we removed something from. And our K changes accordingly. You can write out the expression if you want to. So in our left example here, where we're adding heat, the shift right means more product is being made, so K gets bigger. Questions about any of those three scenarios with Le Chatelier's principle? Here's a picture example of that reaction where NO2 is brown and N2O4 is colorless. So heat is a reactant. If we have an ice bath that this mixture is in, we're removing heat, so we're going to favor the N2O4, that's the colorless side. If it's a little bit warmer, kind of at room temperature, 26 degrees Celsius, then we're going to favor the side that's away from the heat. So there's our summary of how temperature affects exothermic and endothermic reactions. The following reaction is exothermic. What is the effect of increasing the temperature? What is the effect of decreasing the temperature? What side are we putting heat on? We're putting it on the product side. Heat is a product. So we add in our plus heat, and then we treat it just the same as we did for our concentrations. If we increase the temperature of the reaction mixture, we're adding heat. So that will cause a shift to the left, away from the heat side. If we decrease the temperature, that's the same as removing heat. So we will shift right. Towards the heat side. All right, last slide. Consider this reaction. Which change causes a reaction mixture to shift right? Let's run through them one at a time. So for A, we're adding NaCl, increasing the concentration of the product will increase the reaction rate in the opposite direction, so that will cause a shift to the left. So it's not A. If we increase the volume, that would be the same as decreasing pressure. If we decrease pressure, we're going to favor this side with more moles. Or shift to the side with more moles of gas. 3 on the left, 2 on the right. So that will also cause a shift to the left. If we increase the temperature, that's the same as adding heat. It's an exothermic reaction, so we can add heat as a product. If we add heat, that'll also cause us to shift away. And so it's not that one either. Therefore, the correct answer here would be D, none of the above. Any questions about Le Chatelier's principle? You might be thinking to yourself, why is this important? Why does this matter? We're never going to use this. That might be true. You might never use this. But the instances where you would use this is if you have a reaction that you want that has an equilibrium involved in it, and you want to favor either the reactants or the products. So for this example, if we wanted to produce NaCl, there's a couple of ways that we could get this reaction to produce more NaCl. If we're able to remove our product by filtering it or something, right? We can just constantly remove product. That would cause our NO and our chlorine gas to constantly be shifting to the right, producing more product. That would let us use up our reactants. We could pump in more of our reactants. That would cause more of our product to be formed. Knowing that it's exothermic, we could also cool it down. Maybe NOCl is something that we can trap at low temperature to pull it out of the reaction mixture. So that would also be another way that we could shift this to the right. We could also change the pressure or volume conditions to favor the side that we want. So this usually going to have more impacts on you if you actually do end up doing chemistry stuff. Anyway, that'll do it for chapter 16.